presenting my lab on one-dimensional motion for physics. The purpose of this lab was to record and analyze the motion of a real object moving at constant speed, then comparing that result to a computational model based on Newton's second law. As stated before, the purpose of this lab was to analyze the one-dimensional motion of a real object. This object that we used in this lab was a cart, similar to a car that we pushed to move in a constant motion. And we used this object to build a computational model on GlowScript based off of Newton's second law. When recording the motion of the object moving at the constant speed, it didn't change any direction, and we also analyzed that in the video, making sure to use a calibrator on the tracker app. The calibrator will allow us to graph our position versus time graph to represent the object's actual motion. GlowScript is a computational simulation that we use to construct the motion. The model assumes that the net force on the object is zero, which predicts uniform motion consistent with Newton's first law. The predicted motion was then compared with the experimental data to evaluate how well the theoretical model describes the real-world motion. The lab consisted of recording a cart rolling in a straight line using a meter stick to calibrate on the tracker. We also plotted a position versus time and extracted that data to portray a linear line and constant velocity. We then conducted a GlowScript model by coding to match the graph of the tracker to the net force to set it to equal to zero so the velocity remains constant. Newton's first law was the law of inertia, which was the first idea, meaning that constant velocity is when the net force equals zero. Also, Newton's second law, F net equal ma, this is when the net force of an object is zero while the object is moving at constant velocity in a straight line. Here we have a few reasonings. This video shows the object.
You want to roll the car? You want to roll the car, my love?
The system was the cart, the surrounding was the ground around the cart, and the person that was pushing force onto the cart. As you can see, the initial conditions were the initial velocity and the initial position. This here shows the graph of the motion of our object using the tracker. The slope of the line is straight, and here we have the velocity equals 1.12 meters minus the original position divided by how many seconds it took, equaling our slope. In the starter code, we put the ball position to be negative 0.0514 and the vector to be 0.0500. Those were the main changes, as well as while t is less than t8. Here we have the graphs constructed using the GlowScript. First graph is position versus time, starting at 0.5, and then we have the constant velocity chart. The side-by-side comparison shows these graphs, which are both constant, showing that their lines are about the same linear. The computational model and observed data matched. There were a few differences shown in the graph of the tracker because of error from clicking frame points and any wobbling of the cart. The magnitude was 0, which was unchanged between the tracker and the GlowScript. Net force also equals 0, but it doesn't mean there were no forces acting on it because one force was the pushing of the cart. Gravity pulled the cart down, which the group applied friction. Overall, this lab portrayed an object moving at constant velocity, and it showed that it can be modeled in GlowScript by setting the net force to 0. The tracker and computational model both produce straight lines for position versus time graph, with the slope being 0.405 meters per second. The experiment showed us Newton's law in action and how the computational model related to the motion of the cart.